Hello, Hornets. In this video, we're going to be taking a look at differentials. We're going to be talking about what is a differential, how do we find it, how do we use it. Now, first of all, before we start with differentials, I'd like to look at what we already know. Here we have our graph. Notice right here, we have this point on this curve. The curve is the function f, which is I've defined right there. Let me just zoom out just a little bit more. So I have my differential. Now, when I go from a value to a value, I have a change in x and a change in y. And our form for change in x is delta x, and our change is delta y. Now, we've talked about our small changes. Now, when we're talking about these small changes, we call them with a lowercase d, like dx. And because we are using our axis, our delta x is equal to our dx. We said that before as well. And we also know that if I'm looking at this right here, this is an approximate change in y, which we've identified as dy. We've talked about this piece right here. This is our propagated error. And that's the error that we get from using our tangent line to approximate something. And we know this equation because our equation of the tangent line is going to be f of x minus f of a equals f prime of a x minus a. That's our tangent line. And this bit right here, dy, is really the change between what we know at f of a and what we're looking for, in this case, f of c. Now notice that there's a small error between what we're finding and what would actually be. This is the actual answer, f of c. What we're getting is just an approximation. This approximation is what we call dy, and now we're ready to begin. So let's just take a look at our function. If y equals f of x, and I take my derivative, d dx, you'll notice that I get dy dx equals f prime of x. Now watch carefully, because I don't want you to be too surprised. If I'm looking for dy, I move the dx. Oh, okay. So our approximate value, our approximate change, dy, that we've talked about in the past, is simply f prime of x times dx. Okay, well, that's cool. Well, beware, this is the differential. And what we've been doing with it for the last several months hasn't changed. The differential is the approximate change in y. Not the actual is delta y. Now remember, this is based upon what we have already discussed, that the delta x will be equal to the dx by the mathematician's choice. Not only that, but we know that the change in x right here is equal to c minus a. Now this is important to us, because if I'm trying to predict this approximate point, then f of c has to be approximately f of a plus f prime of a times c minus a. And you'll notice c minus a is what we call delta x. So I can then say f of c is approximately f of a plus f prime of a times delta x. And because we as mathematicians have made the claim that delta x is dx, f of c then becomes approximately f of a plus f prime of a dx. And once again, this is dy, the differential. Make sure you can see that. So, the differential is dy. We find dy dx, we move the dx. Not too bad, is it? Well, let's take a look at finding a couple of differentials and make sure. Let's take y equals x cubed. We're going to find our differential. d dx. dy dx is equal to 3x squared. And therefore, dy, the differential, is 3x squared dx. How was that? Now we can do this with any type of equation. If y equals 5x squared minus 7, just made that up. d dx, dy dx is equal to 10x, dy is 10x dx, our differential. All right, let's take something a little bit more complicated. Let's take d dx of y equals sine cubed x squared. Chain rule. Does it change anything? No. dy dx is now simply the complicated 3 sine squared x squared times the cosine of x squared. Whoops, get that squared in there. X squared times 2x. And therefore the dy is 6x sine squared x squared cosine x squared dx. So if you can find a derivative, you can find a differential. And if you can find a differential, you can find an approximation. Let's find an approximation now. We've been able to find our derivatives, or our dy's. Let's now use it. Let's say we know the equation is y equals x cubed at x equals 2, and we want our delta x to equal 1/10. So here's our question. We want f of 2.1. This is an approximation. So the first thing I want to do is find my differential. That's d dx of y equals x cubed. dy dx equals 3x squared. dy equals 3x squared dx. Okay, so here we go. Since delta x equals dx, which equals 0.1, and is the difference between our 2.1 minus 2. Notice c minus a? That's what our delta x is. And since delta x is equal to our dx, we know they're equal. Okay, So that means that I'm going to find my dy at 2 times 0.1. The change in y is 12 times 1/10, and therefore dy is 1.2. This is our approximate change. Now, we know that we started at 2, which gave us 8. And if we plug in and we go to the actual 2.1, we're looking at 21 cubed. And we would have to find out what that is in order to find the difference. But we're approximating our actual value of f of 2.1 at 9.8. And so we're saying it is an approximate value, but we could find the actual value by just using our calculator and plugging in. That's what I'm going to do real quickly. I'm going to go 2.1, the quantity to the third power, and lo and behold, the actual answer is 9.261. Oh, that should have been 9.2, not 9.8. And you'll notice this is an under approximation. We knew it would be an under approximation based upon our graph. After all, if this was a cubic, here's my tangent line, and this is caused by the concavity. Whenever a curve is concave up, the tangent line will lie below the curve. Concave up, below. Concave down, forces it above. And it doesn't matter whether it's increasing or decreasing. It's the concavity. So we knew we were going to get an underestimate. We could see the point was going to be lower than the actual value. And now we can see that it is. The actual value is 9.261, and our approximation, which was our differential plus our known amount, and that turned out to be 9.2. So that's how we use the differential to approximate a tangent line. That's how we find the differential by taking the derivative. And that is what the differential is, the approximate y value change from what we know to what we're trying to reach. How much do we believe the change will be approximately? Thank you very much, Hornets. I hope this has worked for you. I hope you understand this now, and please, I will continue to help you. Thank you very much. Be well, be safe, take care, and